Oops, sorry.
Okay, thank you. Plus star digest. Brian just asked about it. That, of course, is the key feature of the analysis that we are working on. And the bottom line of, when Rodolfo does the first round of analysis using all these data, is really, in some sense, consolidation. So whatever we found previously really seems to be carried still by the data pretty much. So our gluon, for example, changes very little. In other words, whatever we have here as new data sets is always really well described by the previous edition of DSSV. So that's kind of interesting. Digests, we heard a lot about digests at the EIC this morning from Brian, and so the basic idea is, I don't have to explain too much now, but of course digests give you a handle on momentum fractions, lowest order, in fact, from the mass of the dijet pair and the rapidities of the jets. You can reconstruct the X values of the incoming partons that get smeared out by the low corrections, but the information is certainly there. And these are, for example, histograms that I think Star has made showing the regions in momentum fraction that you can access with dijets or with single jets. And you see the dijet distributions typically are much narrower because you have much more handle on momentum fraction. And if you then dial rapidity in a certain way, you can even make the collisions very symmetric or very asymmetric. You have a lot of handle on these things. And Star has presented, I hope this is the latest plot, results for the spin symmetry in dijets. And the red curve is our old DSSV result for that. You can see it still pretty much describes the data quite well. Now, Rodolfo last year actually here at the INT has already shown first results for slight changes in delta G that you get from including those data. And now this is what we showed last year. The green is the really old DSSV, the first one. Blue is the one we published in 14, which sort of gave evidence that gluons are polarized inside a proton. And red is what he gets when he adds the dijet data sample to the mix. So you see, changes a little bit. It seems to go up, if anything, a little bit. The area goes up a little bit too, but no major change really. What's interesting is that there are also now dijet data in really very separate rapidity bins, 0 to 0.8 and 0.8 to 1.8. Again, these three curves you see here describe the data pretty well. What's really curious is that there is a data set now for a bin where both rapidities are sort of forward, between 0.8 and 1.8, and here we really have seem to have some troubles, so we don't get a good fit that would follow this increase of the asymmetry. And I know Rodolfo is working very hard on that and see what comes out of that, whether it can be accommodated in some sense. That's kind of interesting and certainly something that will need to be followed in the future.
So what is actually supports.
Right.
Because of course the kinematic can be that you have a high X quark interacting with low X gluon by going this, and maybe the high X quarks are not so greatly constrained. Just as that was what we were entertaining. Whether that makes sense is a different question.
Right, and whether there's enough room. I mean, yes, the delta U should be pretty well constrained. But maybe because delta U is positive, D is negative, so maybe there's some cancellation.
And we don't have the charge rating on the D, like in DIS. So it could be that it is something, but that was just what we entertained. And
Right, no, good point.
So the difference between those two panels suggests the rapidity.
Exactly.
Separate or
and that would in fact change a little bit the mix of photonic channels. This one has more GG and QG. This one will be mostly QG, where it says a fairly high X quark hitting a fairly small X gluon, that kind of thing, and that could change things.
And you have asymmetric PT kind of all those data sets?
Yes.
Yes, they do.
Yeah, that's always the same. It's just
Yes, it's always 6 and 8.
Yeah, that's important because if you symmetric ones, you run into trouble with large logs, I think. Okay, that's pretty much all I want to say about delta G, and then of course there's the beautiful W data set. I think Ernst will tell us more about W's. I don't know. And then as one of the results that also Rodolfo showed about a year ago already was that, of course, the data for the W minus asymmetry tend to be at the upper edge of things, of previous expectations. And it turns out that, once you look into this regime, it mostly constrains the delta U bar, the anti-quark helicity distribution. And as a result, compared to previous DSSV or other editions where the delta U bar seems to be quite small, here it should be a little higher. And the fit that Rudolf observed last year, in fact, does have a tendency to enhance the delta U bar compared to what we previously had, especially in this region, which is mostly the region probed by the W data. Right, so this will be things to watch out for, and they will come along hopefully over the next couple of months. Okay, that's my update on DSSV, and that's all I can say about that. So now the other two topics, and the first one I want to talk about is something that we started actually already a few years ago with Andreas Schäfer and a by now former student of his. We looked at what I would call a T-odd helicity observable at the EIC, which could be really something new to look at. As you know, we have a lot of discussion over the past decades about T-odd effects in transverse spin physics. This is something that in principle you can compute from first principles, and it's really something that you could verify at the electron-ion collider, which would be just a very neat thing to do, in my opinion. So what's this about? So let's look at brick physics that I just described before, where you have first a PP collision, for example. Then if you suppose that you only have a single initial polarized beam with longitudinal polarization, then you look at a single spin asymmetry, plus minus minus. If this is a completely single inclusive process, like a single inclusive jet production, and if you have all the parity conserving fundamental theories below, then you will get AL equals 0 for a single inclusive reaction. In other words, you can only get AL equals non-equal to 0 when you have parity violation. That, of course, as we just saw, is really used at to W physics in order to constrain helicity. But for any purely QCD probe without any electroweak interaction, we will have vanishing single longitudinal spin asymmetries for single inclusive processes. And the reason why you have that is that the only observer really you can construct in this way is the transverse momentum dotted into the longitudinal spin. And that violates parity. And so,
just to be sure, what is the PTR and what is the SL?
The SL would be longitudinal spin vector of this beam, exactly. And the PT is the momentum of the induced final state, exactly. And this would be parity violating, so unless you have parity violation, you can't have that. Why is it 0? Oh, it's the momentum. I'm sorry. Yes, the momentum should be the full momentum, not PT. Thank you. Good. See, that's why it doesn't work. Okay. Yeah. So now, but then what we got it into, right? But now, of course, if you look at two particle final states, there are more momenta at your disposal. So what you could have, for instance, is a cross product of two PTs now, could be two momenta too, and then dotted into the longitudinal spin. And that is a correlation that that could work in principle. It is parity even, but it is what we call T-odd, right? It's not time reversal violating, but it is a T-odd observable in the sense that we discuss it always in terms of things like the Sivers effect. And now, if you look more closely, you find that in fact there are two possible correlations you could have, and they end up with sinus phi and sinus 2 phi modulations, where phi is the angle between the lepton and the hadron scattering plane. Okay, so you can immediately see that there's some sinus phi dependence emerging, and if you have another term here with the scalar product of the two momenta, you will get a sinus 2 phi. Yeah, so you see that in principle you can have single longitudinal spin asymmetries as soon as you have a more complex final state, right? And that's what made us interested in this. And we
Is it analogous to AL single spin asymmetry that's 3 in Sidis?
Yes, it is analogous to that, except that the one where Hermes very early on started to see the Sivers effect, right? It's indeed something like this, but this is like a perturbative version of this. So you would be looking at high transversal momentum. Whether this has to say something about AL, you will probably. I was thinking about that too, actually, but it would be an interesting thing to think about. Okay, so what are we going to do with this? So of course, if you produce a we produce an affine state lepton and a jet, for example, or a hadron for that matter, and if you use that, then the simplest Born diagrams you can have. The Born diagrams for this process are basically quark-photon scattering, or more precisely, electron-quark scattering. So you observe the electron and you observe one of the outgoing guys producing a jet, right? And so this can have a gluon initial state or a quark initial state. But now, since this is an T-odd effect, you need an absorptive part in your scattering amplitude, and you get that from loop corrections, right? So you need to have a loop correction in order to get such an asymmetry in the first place. And of course, there are loop corrections that are available to us in the sense that, once you go beyond lowest order, you get all kinds of loop corrections, especially you get box diagrams, which are known, of course, to produce imaginary parts. And the idea is simply to compute these and to get the first leading effect for such an asymmetry. And the way you do this is usually you describe things in terms of the electronic and the hadronic tensor. Electronic tensor is unpolarized and symmetric. Hadronic tensor is spin-dependent now. Here's the electronic one, easily computed. The hadronic one is a convolution of Platonic scattering tensor with fragmentation functions and Parton distribution functions. And to compute the Platonic scattering tensor, you would just take amplitude squared for fixed polarization plus and minus, Helicity plus and minus of the incoming partons, right? And then you take the difference and integrate over phase space suitably, and you will get your contribution to the tensor. And rather than computing this, at least at the time when we started this, rather than computing this completely from the scratch, we realized the results can be found in the literature because these boxes and everything have been calculated in related processes in electron-positron annihilation. And it turns out that you can, in fact, by suitable crossing, obtain the results you want from there. We will be in the process of recomputing that completely, but that's a different story. So right now we just take it from there, which turns out to be possible. And when you do that, indeed, this is already the final result. Analytically, you find that your contraction of electronic and hadronic tensor does contain these two pieces. A and B are now perturbative coefficients that emerge from these loop calculations. And I'll just give you here for reference in some sense. They turn out to be relatively modest, simple functions. The logs come from imaginary parts of dialogues because the A plus and minus calculation contains dialogues. And from there you can extract these pieces, and these would be the two coefficients basically that enter into the coefficients of the angular dependencies. Of course, there's an extra price you pay, there's an extra power of alpha strong because it comes from a loop correction, which makes the thing generically small compared to asymmetries that we look at in the first place. But nonetheless, this is an interesting effect, and it's sort of a perturbative version of things that we discuss a lot in terms of Sivers and Bohr-Mulders.
Well, why are they not 8 and 9?
I'm sorry.
Why are they 8 and 9?
Good question, because you can write down the general range structure of the hadronic tensor and you get a bunch of structure functions. And the last two are number 8 and number 9. That's a good, I shouldn't have used that. You're right. Good point. Right, so we did some very early and simple phenomenology for the EIC. The way we do it, we just take a moment of the angular dependence in terms of sine phi or sine 2 phi. Then we average that way and divide by the completely integrated, which is basically the Born processes down here. And so this is what we end up with within the SSV Parton distributions. This shows the sinus phi modulation. As you can see, it's an order 1% effect at best. At best, I'm not sure because we haven't explored the full kinematic set, but this is for a given set of kinematics. Maybe Q squared is a little high. We can play around with that much more. The idea is, of course, or the point is, of course, that this is mostly, we're looking at pi plus produced here, so this is mostly dominated by up quarks. It's also mostly dominated by valence contributions, it turns out. So it's not really the process you would use in order to pin down helicity pattern distributions. I think that's not really the point. You would have much better probes available. It's really there to see the process and to see the T-odd effect in QCD in this way. And this, I think, is exactly. Turns out the asymmetries are relatively little Q-squared dependent overall. Cross-sections, one has to look more carefully here into this, but they are, of course, not very high because you have an extra power of alpha strong that you have, so it must be not so big, but nonetheless, I think very rough estimates would indicate that this should be something that's in principle doable at an EIC. So this might be a neat measurement to make. It's not, the reason why you would build an EIC, but it might be interesting nonetheless. This is pi minus. The sign changes because you're mostly d-quark dominated now, and these are negatively polarized. So you get slightly smaller symmetry, but positive. And of course, we can also look at the sinus 2 phi piece, which turns out to be numerically a little bit smaller, like the size of the sinus phi. So that's something one might be looking at the EIC, might be an interesting topic. Okay, and we'll continue that and hopefully finally write this up. So what's happening here? Did I do that? No. No. Okay, we're back. So this sort of wraps up the first part of my, or the second part of my talk really, and I'm coming now to the final part, which is completely going to change gears now, but I thought this might still be interesting. So I'm going to tell you a little bit about work or about discussions that I've been having with Daniel de Florian, who was visiting me recently, which is about the spin content of the proton that next to leading order and beyond. So what's the point here? So I'm starting from the Jaffe-Manohar sum rule. Matthias gave an excellent overview yesterday about the ins and outs of the spin decompositions. Here is, oh, sorry, that was not my intention. Okay, so this is the Jaffe-Manohar sum rule. And of course, each one of these quantities entering it is Q-squared dependent, right? And so now what I'm going to define is, as always, the first moment of the Helicity PDF, and finally the Helicity PDF comes in my talk. And this gives the first moment, and this is the piece that basically enters the spin contributions here. More precisely, the sigma, the singlet, that is related to the quark spin contribution, is the sum over all F for quarks and anti-quarks summed over all flavors. The delta G entering here is the integral over F over the gluon distribution, which I call FG, right? And so these quantities especially involved with Q squared. And we know the evolution equations in principle for a long, long time. So the evolution of distribution A, and this is always the first moment, so there are no convolutions, nothing, it's always a genuine product. The evolution of the first moment of flavor A is related to the all other distributions, and then there are splitting functions relating the two, right? So the splitting functions are perturbative objects that can be computed in perturbation theory. I'm expanding them, in fact, in alpha A sub S, which is alpha S over 4 pi. And so the first term would be the lowest order, known since 1977. Next order would be the NLO contribution, 2 loops you need to compute in order to derive this. It's something we did in the 90s, late 90s. And then recently, over the last 3 years, the full set of next to leading order kernels has been derived by Andreas Vogts and Moch and Jos Vermaseren, together for a while with the student Rogal. And so now this thing is completely known to 3-loop order, which is next to leading order. Now, the evolution of the angular momentum in the Jaffe-Manohar sum rule, to my knowledge, is not at all known at that order. To my knowledge, it's only known at leading order. Is that still right? Obviously, the sum of the two is constrained by the sum rule. So you know how LQ plus LG would evolve at next to leading order in the sense. But the individual evolution of the two is not known. to lowest order, in fact, the evolution individually is the same as the one for the G that you would derive from the G relation, but beyond that, it's not really known at this point. What I will need in the following is the running of the strong coupling to a given order. So this is the renormalization group equation for the strong coupling. Again, having first three coefficients in the beta function here, it's negative, of course. And as I said before, I should have written it earlier, AS in the following is always alpha S divided by 4 pi, because that's sort of natural quantity that appears in these higher order expansions. Okay? So now let's look a little bit at the splitting functions, and this ties into what Jaffe was talking about it yesterday. So splitting functions you would have for quark flavor K going to quark flavor I by charge conjugation. This would be the same for the anti-quarks. And you can decompose that into a piece that is diagonal in the flavor, plus a piece that is there also for different flavors. So we write it in this way, where the valence piece and the C piece. The same you can do for the anti-quark to quark flavor, which again has a diagonal piece and a C piece. And if you now look at the flavor singlet sector first, because that's the one that really appears in the Jaffe-Manohar sum rule, and these quantities appear there, then of course this becomes a matrix equation, as we know. It has splitting functions PQG, PGQ, and PGG. And the one that appears in the upper left, which connects the sigmas, is in fact related, of course, to these splitting functions. And if you work out the algebra, which is very simple, you find that the splitting function P sigma sigma is just the sum of these two valence pieces plus an F times the sum of these two C pieces, okay? That's just when you write down the evolution. It's not very, very difficult. There's a lot of structure also in the flavor non-singlet sector. If I have time, I'll come back to that at the very end of my talk for a few minutes only. Okay, so now that's what we have. One thing we know immediately is that the first part here, we're only talking about the first moment all the time. This first part vanishes to all orders in QCD, because this first part is what is responsible for the running of the flavor non-singlet charge, which is conserved and which never evolves, right? I'm not showing this here right now, but this is a piece that has to vanish to all orders in perturbation theory. Otherwise, the work in sum would, for example, not be maintained.
Oh, I'm sorry. Looking at the upper right corner of the matrix,
This one?
Huge Cesar.
Yes, I'll come to that in a second. Yes, I'll explain this. So this is the first observation simply, right? So we are left with this piece here. So now let's collect, in fact, what is known. What is known is the following. So this goes mostly, of course, to the latest calculations by which I mentioned, the next to order calculations. I'm referring to the MS bar scheme throughout. So this is the explicit result at one loop leading order evolution. Indeed, as it has a 0 up here. So this piece here is not there at one loop. And as Jaffe just said, the QG vanishes also. Then when you do the calculation, you find the GQ splitting function is just 3 times CF. And the GG splitting function happens to coincide with beta naught, which is the beta naught in the running of the strong coupling constant, which I showed earlier. Okay? So now we go one order higher, which we, as I said, did in the 90s. And the first two entries are still 0. And now the lower left, the PG Q mistake here. This is not lower 0. I'm sorry, this is just a mistake. I think this is not lower 0, right?
Sorry. The two loop.
No.
It's a two
loop. Yeah, it's not.
Two
Yeah, it's just a copy.
Yeah,
Copy. I don't know. Okay. Anyway, so what you find here is a numerical value for the GQ splitting function at 2 loops, and the gluon piece again is the coefficient of the beta function. It's beta 1. And if you go one order higher, then in fact you find a number here, which is I'll show it later, but it has a bunch of color factors, zeta of 2, zeta of 3, many coefficients. It is still a 0 here and has a beta 2 coefficient here. You see one after the other, the beta function coefficients emerge. Yeah, thank you. And so what we conclude from this is 2 things. First, the QG seems to be 0 to all orders. I mean, at least the orders we know them. The GG piece seems to be piece by piece the coefficient of the beta function, which means that what we see here is consistent with PGG being the negative of the full QCD beta function. And the sigma sigma, in fact, and I really apologize for putting the 0 here, it shouldn't be 0, but the PG sigma sigma is indeed related in this way to the PGQ, what you see namely here, and this is the most prominent feature, that in fact these coefficients turn out to be the same up to an overall normalization. And since this is a 2-loop piece and this is a 3-loop piece, you see that there is a relation between the two that evolves in factor of alpha strong. So order by order, it would be shifted to one order.
So instead of the 0 in the upper left corner, 3 CF times negative 2.
Absolutely, exactly. That's the point, exactly, right?
Seems like every talk.
I want to leave that as an exercise, exactly, right?
Like missing
Yes.
signs.
But this is more serious. Anyway, okay, so.
But is that, sorry, but returning to PQ3 being 0, so delta sigma never gets a direct feedback from delta G. Is that something one can?
I come to this right now.
I
think so, yes. And I think, so this pattern we are seeing here, which is sort of summarized by these expressions, is, I think, not completely really surprising. In fact, I think it was already alluded to in very early by Altarelli and Lampe, because the delta sigma is related to the matrix element of the singlet axial current. So it's related to this quantity. And this, of course, is an anomalous current. So the derivative of this current is related to, so it's given by the anomaly contribution, the trace of FF dual. And on the other hand, we also saw yesterday, and we know this for a long time, that you can write this trace as a derivative itself of a current of the Chern-Simons current K, right? And now this means immediately that the difference of JU5 minus 2NF alpha S times K is a conserved current, right? Now there was a long discussion at exactly around that time whether you would be able to associate matrix elements of K with delta G, right? Which is exactly right. Which was Ross, Altarelli, Sterling. They proposed that you have this large negative gluon contribution that suppresses the singlet. Well, it's certainly not really justifiable at a general level. Perturbatively speaking, I think though that in fact, if you go to light cone gauge, these matrix elements do become delta G, right? And it's only that large gauge transformations may break that, and it's not quite clear what happens there. But perturbatively speaking, this matrix elements of this must relate to delta G. And in fact, following the argument, you find immediately, because this becomes basically the negative of delta G, you find immediately that the sum of these contributions should have a vanishing Q-squared derivative. Its conserved current should not renormalize, and it should in fact have a vanishing derivative. So when you start from that now, and you go back into your evolution equations, so then the left equation I just wrote, the left-hand side of the equation I just wrote, you can now insert the pieces, for the evolution of delta sigma and delta G. And what happens is, of course, for delta sigma, you get the sum of these two contributions. Is this? No. So this is wrong, right? What did I do? Come on. Anyway, so talking about this piece, okay, it's just this, right?
That should be 0.
Yeah. Right. So what did I do? Is this right or not?
I think the previous slide said that the derivative was
Yeah. Right. That should be 0 exactly. So right, okay. And so and here, of course, you get an extra piece because you have the derivative acting also on alpha strong, right? And this gives you the beta function. And now for the right-hand side to vanish to all orders, we in fact get precisely the relations that we had been looking for, namely that PGG cancels the beta function, so PGG should be the negative of the beta function. PQG should vanish to all orders, because then it's what was left over here, and then these two should cancel as well. Which
Sorry,
would be
obvious that PGG should cancel exactly.
I mean,
it certainly satisfies gives us.
Right, but you would have an F here, so these pieces have,
there's no
right, there's partly an F in there, but it would be very tricky
You're
to
saying there is an F which gives in the beta function, there is an F used
and then higher powers of an F in here.
Let's look at this slide. But the K mu is gauge. How do we resolve gauge? K mu is gauge dependent.
Yes, but I think
Now does that mean that delta G is KG? Usually,
so I think if you have forward matrix elements in the perturbation theory, I think they will all be KG invariant. I think that was the
unless you have a large gauge.
Exactly. Right.
Right. When the Q square cancels out.
Exactly.
But so that, given that question is still there, how do I see the relation? Can you this can matrix element be engaged? Then how do we get delta G to engage independent?
Right. I mean,
you see what I?
No,
so
I
confused.
understand.
Of course,
Yeah.
now, of course, with the other way, large moment.
Yeah. I mean, I guess you would do it in light
Jaffe,
yeah.
eventually, like what doesn't matter. You don't have the here. It doesn't involve all that out.
Right. Yeah, I wouldn't do that in terms of like the gauge invariant extension or anything. I think it has to be done like convection.
Eventually, it's discussed that the gauge part extension of the
We can, yeah. But it's an interesting question. I mean, it's at the heart of the question, of course.
Yeah.
All right, so we can understand these patterns, and I think, yes.
Sorry, I don't mean to do a shameless plug as an organizer. I shouldn't do it, but in my talk tomorrow, it's not a new result. We've had it for a couple of years. So this is because of Q-squared evolution, but you can look at the evolution in X.
Right.
And we're also seeing, which, I don't have such a nice argument to explain it, but we're also seeing that the quarks, delta sigma effect, the evolution of an object which eventually gives us delta sigma, doesn't get a direct feedback from the evolution of another object which gives us delta.
Right.
So it's just a comment.
Right.
Yeah, it's not a Q-squared evolution of the difference, but maybe there is.
Right, and that must be related. Yeah. Could be interesting to see. Okay, so now we have this relation, and now of course we can push it in order higher, because the thing is, this relates a previous order to next order, right? So if you know this guy to two loops, which Moch and Vermassen and Vogt have computed, then you know suddenly, which is three loops, which is NNLO, then you suddenly know the evolution of the singlet to four loops, which is quite impressive. And so this is the piece now that Moch and Vermassen and Vogt have calculated, and multiplying it by -2NF would give you then the for loop evolution of the singlet, which is kind of cute, I think.
Can you use a beta function to get PGG?
Right, exactly. Exactly. So you just use that to cancel, because in the evolution of P, you just assume that this cancels out.
I mean, if you really trust it.
Yeah, exactly, right. So that means, in fact, if you look, that means that a single anomalous dimension controls basically all evolution. PGG is given by the beta function. PQG vanishes. PGQ and P sigma sigma are related. So that means immediately that once you multiply the gluon by alpha strong, then its evolution is entirely determined also by the singlet anomalous dimension, right? So things become, in some sense, very simple. And if you add up these equations, you immediately come back to the old anomaly equation I was giving earlier.
Is that just a ID theory?
Yeah, right. I mean, of course.
You cast it in such a way that it couples with that.
Exactly. So that's exactly right. That's, I think, what really Altarelli and Lampe realized at the time. So that because the anomaly condition is really not renormalized, gives rise to this kind of. So that's kind of interesting. It's actually very straightforward to solve these equations analytically to the order you want, because this is a simple equation. You write down the evolution immediately, and then you just insert it here and integrate, and you get the other equation, right? So if you do that, for example, here's the evolution of the singlet. This is the expression you get. You could expand the exponentials to the desired order, but this is sort of exact solution to the truncated perturbation theory equation. And what you see then is that if you normalize to the lowest order, then the biggest part evidently is from the NLO evolution, which is the two-loop piece, and then the three-loop piece adds a little bit more, but now the four-loop piece really makes a tiny adjustment to that. So this really converges very nicely. I should mention that some years ago, these gentlemen looked at the NLO evolution already. That was about, I think, 2000, and this in fact is Henley, Ernest Henley from here, from Washington. He was involved in that. K is basically the K factor. It's the delta sigma at the higher order divided by the one at lowest order. Right, so you see the evolution is quite mild, of course, and And the fourth order is really quite small. If you were brave enough, so we start here at 1 GeV, if you were brave enough to push that down to smaller scales, and of course the thing will explode very quickly. And so in that sense, you could, at low scales, find something that accommodates a large value of delta sigma, because when you run back, it will always go up, become large. Whether you like that or not, or whether I like it or not, I'm not so sure. Finally, you can also solve the equation for the gluon spin, of course, which is very simple. After all, it's just this guy here integrated over the right-hand side. And the one thing I want to point out is, after integration, you basically get a function for the right-hand side that comes from the integration. You can write down order by order. It's not so important right now how it looks like. But one thing that's kind of interesting is that if you look at just the lowest order evolution, you have these two pieces. And you can see that there is a piece proportional to alpha strong at q squared. And then there are two pieces, this one and this one, that are sitting at alpha s of q naught squared. And so that means, if you divide out alpha s, then the gluon spin contribution will, of course, rise as 1 over alpha s of q squared. It can go up or down depending on the input. If you fine-tune the input such that this piece here cancels precisely this piece at the input, then the alpha s will cancel out and the delta g will remain flat with q squared. And this happens, in fact, by a value of roughly minus 0.1. So it's in some sense like a fine-tuned input, or in some sense like an artifact or a cute feature of the equations. You can work it out to higher orders. You can always find an input in such a way that the gluon stays almost constant and goes asymptotically against the constant, at least. Whereas in every other input, it will either diverge as 1 over alpha s or go to the negative 1 over alpha s. Okay, so that's kind of an interesting feature, and this value is always around this value. So every order you find values of this size. It can be minus 0.12 or so, but it's really very close. Finally, just last 2 minutes, I'm going to briefly mention the non-singlet sector, just to put it into perspective for what Jaffe said yesterday. These were the equations I wrote down earlier, which sort of split things into valence and the C part. And very briefly, the diagrams that enter the splitting functions to contribute the following. For QQ, of course, you have something that is already there at lowest order. It's just a simple diagram where the quark radiates one gluon. To get something that turns anti-quarks into quarks of the same flavor, you need a diagram like this one, which is a two-loop diagram. So you only have this contribution here for the first time at 2 loops. To have something that converts Q to Q and potentially for different flavors, you need a diagram like this one. And this is sort of the disconnected insertion that Jaffe was talking about yesterday. That's the terminology, of course, from the lattice, but you can see basically that there are two separate quark lines. And in the lattice, of course, there will be tons of gluons connecting this. In the perturbative language, this is a contribution that for the first time appears at 2 loop, and that allows the flavors to be different also here and here, and this is why it contributes for the first time. If you go 1 order higher to 3 loops, then in fact you have an interesting feature that you can, of course, exchange 3 gluons here, and you can sort of create a C-odd effect, which means that once you go to 3 loops, then there's a difference between these splitting functions even. That was even noticed already in the unpolarized case years ago. And this difference generates, just perturbatively, a difference in the strange and anti-strange distribution. For that to work, of course, the proton has to be also different in quarks and anti-quarks, but it is, of course, because it has more quarks than anti-quarks. So the valence distribution of U and D drives this valence strange distribution that you would generate perturbatively. Non-perturbative effects, of course, should be bigger, we would hope, but at least that's what creates a perturbative effect. So this comes entirely from 3-loop diagrams of this form. And this is, of course, present also in the polarized case. There's a difference in the sense that in the unpolarized case, of course, the net valence number of strangeness must be 0. So in the unpolarized case, the first moment of the splitting function has to vanish so that you don't generate a strange valence distribution. In the polarized case, there's no such constraint. And so therefore, in fact, when you work it out, you find that, in fact, this effect creates an antisymmetric strange, anti-strange distribution for the first moment. You can compute that. It again is, of course, a function of the first moments of the valence densities. And then you can estimate that and investigate its running. It's a very small effect in a sense, as you would expect from three-loop contribution. So assuming that the asymmetry just vanishes at q squared equals 1, it will asymptotically reach something like a 0.1% effect. That is, of course, evidently much smaller than the strangeness itself that we get from perturbative analysis, and may hopefully be a lot smaller than any non-perturbative difference in strange and anti-strange. Nonetheless, the effect is there, and it turns to a negative delta S minus delta S bar asymmetry. And I think that's it. All I wanted to say is a sort of mixed bag of things. Our DSSP upgrade is in progress. I hope there's some interesting opportunity to do sort of Helicity T-odd effects at the EIC. And we know a lot, I think, nowadays about the evolution of the proton spin content at higher orders. Thank you very much.
Questions? Comments?
You mentioned that we get to OAN.
Yeah, right.
You have a,
yeah, so
splitting functions.
yeah, right now. So what's happening? What exists is, of course, right now you could take the sum of the two, and you could just whatever. If you have three-loop evolution for the spin piece, you can derive the three-loop evolution of the sum of the two. Right? However, if you want to have individual evolution of quarks and gluons exactly, then of course you would, then you would need to evolve them separately, and you would need to know, you would need to know the evolution of them individually, right? And that's only known to lowest order. That was done by Heckler and Schäfer and Kundu and other people. And so that's all that's known at the present.
But you have plans to?
Yeah, we will compute that. That's our plan, definitely. And yeah, it should be interesting to see how that works.
We can do both canonical, so Jaffe-Manohar, and kinetics would be the G.
Yeah, that would be
the LG,
right.
And gluon would be also related.
Yeah, right. I mean, I would expect really that you start seeing a difference in evolution, say, of LQ between Jaffe-Manohar and G, right? And it'd be really interesting to see how, how this effect comes in, right? If you want to be really serious, of course, you would have to decompose also this into flavor singlet and non-singlet contributions. The singlet is what matters here, but of course, for full evolution, you would have non-singlet contributions and so forth.
In connection with the EIC and the T-odd observatory. So,
yeah.
This is also called quark and gluon Helicity distribution, right?
You could, yeah.
Now, the naive question that I'm having is, okay, why is that the unpolarized cities? Polarized 3D-dependent cities cannot be used as a vector. So somehow,
right?
No,
yeah.
I mean, connection with the talk that I gave last week, the only difference is just polarized.
Yeah, I mean, as I said, I mean, you will have much better probes at the EIC to get the Helicity distributions, right? This is in some sense like a,
yeah. Whether someone has done that study, like projection.
Oh, I don't. No. I mean, yeah, somebody should do that. Now that you have your NLO calculation, you can do it.
But even at LO,
right.
Nothing special about the NLO. Even the LO.
That's true. Yeah.
Some non-zero.
Yeah. Right. We looked at that long time ago, again in the wake of the sort of EMC spin crisis, because at that time people were saying maybe there's a large gluon piece at order alpha S that enters delta sigma, and then quite naturally people started to compute photon gluon fusion to QQ bar, one of them becoming a jet or fragmentation. That hasn't been revisited much since then, I think, but should be done. Yeah.
That's how we.
Yeah, I think there's papers in that.
Yeah, very nice talk.
Thank you.
But I just want to verify the maybe semantics. When you need a delta S symmetry,
yeah.
You mean it's not some symmetry is broken, right? Just because the target is
exactly right, because that's exactly the thing. So it only, as you can see from the solution, really, you can see you have to have more quarks than anti-quarks, or vice versa, in the target, right? And if you don't have that, if there's no U minus U bar or U minus U bar, then the right answer is 0. Otherwise, it's anyway small.
No other questions?
Okay. So this sample that you have there, well, it's sort of a sample, right? This combination that cancels out the.
Yeah.
So is there any, I mean, I'm just thinking about that since in PDF we don't have samples like in the Polarized case.
Right.
Can we take that in as advantage? Is there any way to pull out that combination from somewhere else? Or
no, I think
no,
I don't know. I haven't any insight into that. I think the nice thing is that you need this. Let me go to this one. That you need this to one order lower than the other one, so that helps you to. So if one day Vogt and Fermat will more do a video follow calculation of PGQ where delta sigma at 5 loops, but I don't know. Yeah.
Assuming that we know that quantity in the range, suppose we know that number, then we have less, and we can remove the normalization of delta X.
Right. Yeah. No, yeah, but yeah, I don't know.
No connection with anything. No.
Not anything known to me. Maybe you have an idea. Good question.
All right, thank you very much.
Okay, thank you.
The last one by Ernst Sichtermann.